Okay, so let's review last time. Last time we saw Mellin transform and inversion. Mellin transform and inversion. So if we have a nice test function f is a function from the positive reals to C, then we can make a Mellin transform of it by taking f, multiplying it by a character t to the s, taking dt over t, and integrating. And we have to worry about whether this will be meromorphic or holomorphic and so on, depending on what's going on at the endpoints, right? And we have Mellin inversion, so that's the transform. This is the transform. The inversion formula is if you take the Mellin transform of a function, you multiply by t to the minus s, so the opposite character. It's not really the conjugate because, well, it is the conjugate. It is the conjugate. T is a positive real number. No, it's not the conjugate because I'm taking, it's not the conjugate, right? The conjugate would be s bar. So I'm also taking the same real part. I mean, I'm negating the real part as opposed to conjugating. ds, and you integrate over a vertical line, like this means from 2 minus I infinity up to 2 plus I infinity. And of course, we always have a 2 pi I floating around. That will recover the original value of f, and that's the inversion formula. So far, so good. That was last time. We saw the example of the gamma function, which is originally defined in the case of ft equals e to the minus t, t to the s, dt over t. We also saw that gamma of s plus 1 is equal to s gamma of s, which allowed us piece by piece. So originally we're only defining this half plane. We have a pole here, but then we piece by piece analytically continued it back, getting simple poles. So this has meromorphic continuation with simple poles at s equals 0, -1, -2, -3, and so on. So far, so good. Okay, some other things. A key ingredient, so there was an ingredient in this proof, although it was a fake ingredient, but here's another sort of example of a Mellin transform and inverse pair. So what about f of t? We saw this last time. Maybe I didn't emphasize it enough. The indicator function of the interval 0, 1. What is its Mellin transform? Well, you integrate from 0 to infinity the indicator function of 0, 1, t to the s, dt over t. So this, of course, is just the same thing as cutting the integral to go from 0 to 1. And t to the s minus 1, I know how to integrate that. That's t to the s over s, evaluated from 0 to 1. Of course, as long as it converges. This is only if it converges. And for it to converge, I need s minus 1, the real part of s minus 1, to be at least -1. In other words, the real part of s has to be bigger than 0. Does that make sense? And at 1, this evaluates to 1 over s, and at 0, it evaluates to 0. So I just get 1 over s. Does that make sense? And let's check the inversion formula. The inversion formula, inversion, would tell us, if we use this function. So again, you see why we need the real part of s to be bigger than 0. This has a pole at 0. So this makes complete sense. This has a pole at 0. So in order to evaluate this integral, we need the real part of s to be 0, to be bigger than 0. But of course, it also has analytic continuation, meromorphic continuation everywhere except 0. What about the inversion formula? That would say 1 over 2 pi I, integral over some vertical line like 2. F tilde of s is 1 over s, and then t to the minus s, let's call that t to the minus s, ds. Well, that was exactly that integral. This is called Perron. We did this integral last time. I think I didn't. This is called Perron's formula. Does anybody remember what this comes out to? One of two things. This will play a key role in what we're about to do. It already played somewhat of a role, right? This doesn't converge absolutely, so you have to be quite careful about what you mean by this. But you remember what we did? If t is bigger than 1, I guess this is 1 over what we did last time. If t is bigger than 1, then if I pull the contour to the right, then this thing is going to 0. And there's no poles. This was pulling contours right, pull right. So here's the kind of vertical line 2, and we just pull the contour to the right, and there's no poles. And so it just dies. And if t is less than 1, then we pull the contour to the left. We pick up a residue at s equals 0, which evaluates to 1. Here's our residue. I'm just reminding you what we did last time. Hey, look at this. What is this function?
It's the indicator function.
It's the indicator function. It's exactly what we started with. Of course, that's what we should get. This is the indicator. This is f of t, namely the indicator function of 0, 1. These are open. Well, I don't care about what happens exactly at 1, something funny happens, because of course this isn't even continuous, so we have all kinds of other issues. But okay, I'm just reminding you some things. What else? And we talked about Gauss's conjecture, and we're headed to some good stuff. Good. Let me try to illustrate this phenomenon. That's what I just want to show you. Let's see if we can see why this kind of thing is happening. So this is an attempt to illustrate that. So I'm taking, if let's say t is 3/4, okay? So if I take t to the minus s, and s is 2 plus it, okay? So this is t is equal to 3/4 to the minus s over s. And I just want to know what this looks like. Let's go, let's see the whole thing, plot range all. So t is less than 1. Can you guys see this? So look at what it does. It has this little, and we're integrating this. So we're sort of adding up all of these values, right? With a 1 over 2 pi I. I guess I can divide by 2 pi I as well over 2 pi I. Maybe that's better. I don't know. Is that better or is that not better? Well, don't worry about this constant. You see what this is doing? Effectively, it has this loop. It has this loop, and this loop contributes, since t is less than 1, this loop contributes a main term, and then it just cycles, and all of the cycles kind of cancel out, but they don't cancel out in absolute value. I'm just trying to give you some other heuristic explanation for why this is happening, as opposed to if I put in a number greater than 1, if I put in a number greater than 1, like 5/4, now the plot, instead of having this this loop, the plot just has a circle, and believe it or not, all of these values still add up to 0. So the total integral if t is bigger than 1 is 0, whereas the total integral if t is less than 1 is not. Let's see. Can I share the entire?
Oh, okay. T in there, in that expression, parameterizes S.
Yes.
Okay.
Yes. T here. Oh, I'm sorry. Yes. Yes. Maybe I should put an X here. Will that be better? If I call this X, let's call this X. 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 have an eraser. Or u, maybe u is even better. U to the s, u. Yes, I'm sorry. I'm using t for two different things. U to the s, du over u to the s, yada yada. Okay, good. Okay, so you guys can see this. So the point is, if u is bigger than 1, then this thing is basically canceling out on top and bottom and side to side, and so the total integral is 0. Whereas if u is less than 1, that's when it has this extra excursion, which is not canceled out by anything. And that's, all right, that's Perron's formula in a nutshell. You buy it? Okay.
Just out of curiosity, does that like sort of cross come from the right side or the left side, so to speak? Like if you put u close to 1.
So if I make u very close to 1, so let's make u from below or from above. Let's make it 399/400ths. So it has a little, it's having trouble deciding whether 399/400ths is less than 1 or greater than 1. But it is less than 1. And so it's sort of doing all of its spinning over here. In fact, it's what people often do is the value of u equals 1, they set to 1/2. This is, again, all of this nonsense is coming from the fact that this integral isn't actually well defined, because it doesn't converge absolutely. So you have to do this in symmetrically and play all kinds of games. But let's see, if I do it slightly less dramatically, so you can still see over here is the looping, is where it's starting to loop. You see, I only went out to 100 in the imaginary part. And if I go out farther, then you start seeing the looping. But the closer u is to 1, the longer it takes to see looping one way or the other. So if I go to the other extreme, or on the other side of 1, if I go 41/40ths, well, gosh, how do you tell between this and this? You can't at this scale. Does that make sense, Thomas? You have to go out quite a bit further before you see a difference between these two. And I think it's very hard to see that difference at this scale. Yeah, see this one's winding around over here. Here u is less than 1. So it's winding around, but not enough so that this excursion doesn't contribute a total of 1 in the end. Whereas this one's winding around on the other side, and it will eventually get you a balanced average, 0. Okay, let's go back to work. All right, so I just wanted to show that little bit of Perron's formula, because we'll need it in our upcoming discussion of Gauss's conjecture. And this, maybe I should also say Legendre-Gauss, since Legendre was thinking about the same things. It's not fair to give Gauss all the credit, although many books do. The Legendre-Gauss conjecture is that, again, the number of primes up to x, this is the number of primes up to x, is conjecturally asymptotic to the logarithmic integral of x, which, if you recall, is the integral dt over log t from 2 to x. And we sort of saw that this pi is some kind of step function like this, pi of x, and then lie, which is asymptotic to x over log x, well, it's some nice curve. Okay, so this is what we're headed towards. Now, I need to remind you of a couple of more things. So, and recall one more thing, I guess, at least one more thing. If we have a nice test function on the reals, we have Poisson summation, the Poisson summation formula. Does anybody remember what it says? If we have a nice test function on R, on all of R,
sum over the integers of its value at the integers is equal to the sum over the integers of its value of its Fourier transforms.
Beautiful.
Is there a corresponding version for Mellin transform?
There is, and there's even a better version that we're about to see. What we're about to do is give a Poisson summation formula on the primes. That's what we're trying to derive. Okay, and you remember if we make if t is positive and we set and f of t of x is, let's say, f of, how do I want to do it? F over t or f times t? Let's do x times t. Then, do you remember what f hat of t is? Colin is asking, is there homework for next week? There's homework due Tuesday. And the homework due Tuesday will be to do the exercises from last lecture and this lecture. Does anybody remember what this is? Okay, so I'll leave this as an exercise. Good, that reminds me I need to give you exercises. So these are exercises to be handed in. Exercise 1 is that this comes out to the original Fourier transform, but not xc, but xc over t instead of xc times t, with an extra factor of 1 over t. So that'll be a good refresher of the Fourier analysis section. Okay, so if I apply this statement to the Poisson summation formula, I think we discussed this at some detail, that f of n times t is equal to 1 over t sum over m of f hat of m over t. Right? You guys remember this? We talked about like the case of the Gaussian, which will reappear here in a minute. This look familiar? Great. Okay. So now let's make a little assumption. Assume that f, this test function, is even. Does anybody know what that tells us about the Fourier transform? You remember? Is it even or odd? Am I going too fast? Nick?
Wait, what happens with the character?
I want to say odd.
I'll say even, so we get differing opinions.
Okay, the answer is even. Okay, so this is exercise 2.
It is, okay, yeah.
Exercise 2 is this. Good. We're collecting a list of exercises. It turns out it's even, well, okay, I won't do the exercise for you. And what that means is that this thing we can write as, well, there's a value at 0, nothing I can do about that. Plus, I can group the positive and negative values together because they give the same contribution. Are you happy with that? So this thing, by the way, I could have given it a name back here. This thing is often called, well, maybe I'll call this the theta function. Okay, so this I will call theta sub f of t. Okay, you give me a nice test function. What I'm going to do is add it up over the positive integers of f of n times t. Of course, it needs to be rapidly decaying and so on. What does Poisson summation tell us? It tells us that this sum is equal to, let's see what happens on the other side. So there's the value at m equals 0, which is still f hat, I guess there's a factor of 1 over t, f hat of 0, plus, and again, it's even, so I get to add up twice the sum over the values of m greater than 1 of f hat of m over t. Whoops, and there's a factor of 1 over t in front. Okay, does that make sense? So let's see what we can learn about this function. so let's say f has exponential decay, or okay, let's do an example. Example, and this is the classical theta function. The example is f of x is the Gaussian. Gaussian. What's the Fourier transform?
The Gaussian itself.
Yeah, it's itself. It's the same. Okay, so what do we know about, so theta for this f, theta f of t is a sum, n goes from 1 to infinity, e to the minus pi nt squared. So this is n squared t squared. So what do I know about the behavior of this function? So at infinity, as t goes to infinity, this thing, what can I say about it? Okay, exercise. Good. Exercise. This is exercise 3. By some simple inequalities, you can show that this thing at infinity is bounded by, let's say, some constant e to the minus t. So we have exponential decay. This is as t goes to infinity. Okay, do you buy it? This is a very weak statement. Significantly stronger things are true. In fact, it goes like e to the minus t squared, but never mind. Look, the first term here, the first term is already e to the minus pi t squared. So if t is bigger than 1, you're already way, way smaller than what I've claimed. Okay, but I'll let you think about that. What about as t goes to 0? So remember, I took t, this parameter t was positive. So this is a function, it's supposed to be a nice function on 0 to infinity. So we took the real valued function f, and we've turned it into a theta function, which we want to think of as having values in the positive real numbers. So as t goes to 0, what can we say? Well, now it's very hard to say. Each of these terms individually is going to 1. And now we're adding up 1 infinitely often. So what's going on? Bless you, Nick. Well, it's too hard to say from this perspective. What should we do if t is going to 0? Where should we look? If only we had some other expression for this theta function.
So is the idea that if you do a reciprocal thing of a t's, when t gets smaller, v ever gets bigger, or something like that?
Yeah, just look on this side. On this side of the equation, this thing is decaying exponentially. So as t goes to 0, let's see, how should I write this? Theta f of t, I guess I'll move this to the other side and I'll divide by 2, is equal to 1 over t, a sum n bigger than 1 f hat of m over t, and t is going to 0. So that's the same behavior as we had here. And then plus 1 over t f hat at 0, and then minus, I divided by 2, and then minus f hat of 0 over 2. Does that make sense? That's just an identity that holds for all t.
You mean f of 0 over 2.
I'm sorry, thank you. F of 0, no hat here. Thanks. Does that make sense? And so this part is decaying exponentially. This part's blowing up. So what happens to this as t goes to 0? What happens when you have exponential decay times polynomial growth? Yeah, Yeah, this is going to 0. This is a constant. And this, well, it blows up. It does blow up, but it blows up like 1 over t. Okay, so what we can see is that theta f of t, it does blow up as t goes to 0, but it blows up only like 1 over t as t goes to 0. Okay, does that make sense? So far, so good? So here is the key idea in Riemann's memoir. Key idea in, he doesn't do it exactly this way. This is sort of a reinterpretation, a modern reinterpretation in Riemann's memoir. In fact, we'll do it really, well, not that modern. So this is following Tate's thesis. I'll try to explain where the Adels come in or not. So this is the 1859 memoir of Riemann, is to compute the Mellin transform of a theta function. Okay, so this is called a theta function. This is a general theta function. Okay.
Is that
Go ahead.
is that thing as t goes to 0 just for the Gaussian? I feel like I remember something about Fourier transforms always being exponentially decaying among the class of functions you're considering.
In nice classes, that's exactly right. So I haven't been careful about what class of functions I'm taking now. Now I want to just talk in general terms, and whenever things converge nicely, you're allowed to do this. One example of when it converges nicely is the Gaussian. And there will be other examples, but for now, you could even take compactly supported functions, because then their Fourier transforms will also be entire, and you can pull them in various directions and so on. But you're absolutely right. If we use the classes that we use for Fourier analysis, where the Fourier transform has exponential decay, we need more than polynomial decay for the function itself, which is all we assumed. We assumed like 1 over x squared decay. That's not enough to conclude things like this. This is just in the example of the Gaussian. We have this behavior. But in general, this is kind of a general phenomenon as long as the original function had enough decay, like exponential decay. Great. Okay, so let's compute this Mellin transform. So we take our theta function, and we're going to compute the Mellin transform of this thing at S. Okay, so we sum. What is a Mellin transform? It's an integral from 0 to infinity. I want to see the theta function. I guess I have it here. I want to see it here. Sum n greater than 1, f of nt. That's the theta function, times t to the s, dt over t. So far, so good? Where does this, in the case of the Gaussian, where does this converge? Real part of s greater than what? At infinity, is there any question about convergence? At infinity, we have exponential decay, and this is only polynomial growth. So we're always fine at infinity. How about at 0? This thing blows up near 0 like 1 over t. So now I have t to the s minus 2, and t to the s minus 2 is integrable near 0, is integrable if and only if the real part of s minus 2 is at least -1. Does that sound right? So you need to be going to 0. Near 0, you need to be blowing up no faster than 1 over t. And so if I move the 2 to the other side, real part of s has to be bigger than 1 for this to converge. But in that region, it converges absolutely, and there's no problem interchanging orders and stuff like that. Okay? So if the real part of s is greater than 1, we have no problem interchanging orders. Interchange. Summation and integration. We have absolute convergence. Okay, and then we have an integral from 0 to infinity, f of nt, t to the s, dt over t. So far, so good? Now I want to make a change of variables, and you're going to start to see why I want this, why this really is the Haar measure. I'm going to remind you that this is Haar measure, invariant measure, as you'll see in a number of computations. So, okay, I want to set y, I'm going to make a change of variables, y equals nt. N is fixed. This is a change of variables in t. So dy is equal to n constant times dt, constant bigger than 1. And so dy over y, there's an n dt over nt. The measure is invariant under the group action. Cool? Okay, let's keep going. So this is a sum over the positive integers, integral from 0 to infinity. So I'm replacing nt by y. So this is just f of y. T is y over n. Y over n. Because this is a character. And that's how characters work. This is a character. I'm trying to emphasize the general nature of this calculation. Okay, you know that y over n to the s, y and n are positive real numbers, so there's no problem with pulling the n to the 1 over n to the s out of the integral, since it has nothing to do with the y's. And dt over t is dy over y.
Wait, what's the crucial part of being a character that you mentioned?
Well, that being a character is, I'm using the fact that, well, I'm not using that it's a character, I'm just using the fact that we can do this, that this is how multiplication works and exponentiation works. But this is a general, this is sort of cheating, because there's a more general principle, and the more general principle is that the thing, the t to the s there is a character. And that's why this is happening. Okay, now what? What do you see? Is there any more n in this? It's totally independent of n, and in fact, we can recognize what it is.
Looks like a Mellin transform to
Looks
me.
like a Mellin transform. Looks like a Mellin transform of f. And what's left over?
Zeta.
Zeta. And that's it. That is the miraculous calculation. That's the beginning of the miraculous calculation. So this is for a real part of s greater than 1, where all of these things converge. That is the miraculous calculation, the first miraculous calculation in Riemann's memoir. So far, so good? Okay, so let's write this again. For any nice test function, f tilde of s times zeta of s is equal to this integral from 0 to infinity of theta f of t, t to the s, dt over t. Okay, by the way, okay, I'll come back to that. So then he says something else. The behavior of this function is very nice when t is large. But when t is small, we have this problem. So let's break the integral as an integral from 1 to infinity, where we want to leave things alone, plus an integral from 0 to 1, where things aren't as nice. And is there another version? So again, this is an integral from 1 to infinity of the theta function, t to the s, dt over t, plus on the integral from 0 to 1, instead of theta, I want to do something that has nice behavior near 0. What has nice behavior near 0, unlike theta? Now you can see it. Yeah, Nick, go ahead.
Use the other one.
Use the other one.
There, that.
Use
Yeah,
the other one. Okay, so I'm going to put 1 over t. This is actually theta, not for f, but for f hat, not at t, but at 1 over t. Does everybody see that? Can you see this, or is it getting too small? Anna, can you see it? Yeah, okay, great. Minus, plus 1 over 2t f hat of 0. Can I fit it in? Minus f of 0 over 2. So now let me zoom back in. F of 0 over 2. F of 0 over 2. Okay? Does everybody see that this is just an equality? Alrighty. Now these integrals I can actually compute. So again, we have this outer integral f theta f of t, t to the s dt over t. Nothing wrong with that. Plus, now let's look at this integral. That's supposed to be a 1, right? 1 over t f theta of f hat at 1 over t, and t to the s. Let me write it one more time before I mess with it. Integral from 0 to 1, 1 over t theta f hat at 1 over t, t to the s dt over t. Okay, so I haven't done anything with that. Plus, okay, now we can actually evaluate these integrals. There looks like there's an f hat of 0 over 2 times an integral of t to the s minus 1 minus 1. So t to the s minus 2 integrates to t to the s minus 1 over s minus 1, evaluated from 0 to 1. That look right? Minus, now I'll do this last integral, f of 0 over 2. And now all I have is a t to the s minus 1. That integrates to t to the s, evaluated from 0 to 1. So far, so good. Who's with me? Thumbs up. Thomas, I'm starting to lose you. Where am I losing you?
I'm just copying everything down.
Okay, but it makes sense? Oh, you just need time to copy things down. Okay, I'll give you a minute. Give me a thumbs up when you're good to go.
Professor, is it t to the power s by s?
Thank you very much. Divided by s. Thank you, thank you, thank you. T to the s over s, that's crucial. Thank you. Okay. All right. What do we want to do on this integral? This doesn't have nice behavior. It has nicer behavior as t goes to infinity, not as t goes to 0. Let's make a change of variables. Theorem, you got to change your variables for us?
U equal to 1 over t.
Perfect. So what is dy? I guess it's negative 1 over t squared dt. Whoops, dt. So what is dy over y? Negative 1 over t squared dt over 1 over t, also known as, one of these cancels, negative dt over t. Aha. Par measure. Okay. So this is equal to, there's still this term in front. In fact, maybe we can do a little bit more before we do. So this integral, let's just play with this integral. Instead of 0, if t is 0, then y is infinity. And if t is 1, then y is 1. 1 over t turns into y. This is theta f hat of y. T to the s is y to the minus s. And then dt over t is dy over y with a minus sign. And the minus sign will let us flip these in the right order. And now we can actually combine the first two terms because they're of the same general shape. We have an integral from 1 to infinity. I have a theta f of t times t to the s plus a theta f hat of, let's change the variable back to t, times t to the 1 minus s dt over t. Does everybody see that? And then what's left over is plus, at 1, I just get 1 over s. So let me write this actually in a funny way. I'll write it as a minus to illustrate a point. F hat of 0 over 2 times 1 minus s instead of s minus 1. That's what I'm doing with that minus sign. Minus f of 0 over 2. And this integrates just to s. This value is just to s. And this was all equal to f tilde of s, zeta of s. Okay? So check out this function. What do we know about this function? We are integrating from 1, where theta is nice and compact, so there's no problem with any of these polynomials near 1. I mean, 1 is, we're in some compact region. Out at infinity, both of these have exponential decay, so they beat out whatever polynomials are next to them. This function is completely entire. We've gone away from 0. 0 is where we had trouble. This is entire in all of C, defined over all S, all complex numbers S. This is, I mean, just 1 over S. This is a simple pole at S equals 1. And this is a simple pole at S equals 0. But these also are meromorphic functions. So this whole thing, this left-hand side is completely meromorphic. And if f tilde has analytic continuation beyond its initial domain of convergence, then we've given meromorphic continuation of the zeta function. In fact, let's go one step farther. So this would give, so this thing is meromorphic on all of C, which means it gives analytic continuation or meromorphic continuation, analytic continuation of this product at least. So if you can work out what f tilde is, then you've given meromorphic continuation of zeta itself. Cool? Let's do one last calculation. If f of x, again, is e to the minus pi x squared, this Gaussian, then let's compute this Fourier, this Mellin transform. What is the Mellin transform of a Gaussian? This is a quick computation, e to the minus pi x squared, x to the s, dx over x. Is there a change of variables that seems reasonable to you guys? Like, I don't like this pi x squared here. I would be much happier if that was just a e to the minus t. Well, let's call it pi x squared then. So what is dt? what is it? 2 pi x dx. Does that look right? And so dt over t, you will love this Haar measure. Without this Haar measure, all calculations, if you actually write this as t to the s minus 1, all the calculations, they're like god awful, but then at the end, they magically cancel out. It completely obfuscates why they magically cancel out. They magically cancel out because this thing is Haar measure. And if you square the real numbers, the positive real numbers, you still get all the positive real numbers. And if you multiply by pi, you still get all the positive real numbers. So dt over t, okay, dt is 2 pi x dx, and t is pi x squared. So I'm left with a 2 dx over x. It's again dx over x. Okay, this is invariant measure. So let's just finish the calculation and then we'll take a break. So the integral is still from 0 to infinity. Now I have an e to the minus t, x to the s, x, I guess I have a t over pi, and then I have to take a square root. There's no problem with this square root. These are positive real numbers. So x is t over pi to the 1/2 to the s, and then dx over x is a half dt over t from this. Okay, so the 1/2 I can pull out. There's a pi to the minus s over 2. And what's left over? What's the dt integral?
No, gamma function.
Gamma function at
S over 2.
s over 2. And so let's look at what we just proved. We proved that 1/2, so now I'm going to plug this in here. 1/2 pi to the minus s over 2, gamma of s over 2. Gamma we know has meromorphic continuation, times zeta of s is equal to, let's read this formula. Let's read this formula. I have an integral from 1 to infinity. By the way, what is the Fourier transform of the Gaussian? It's itself. So I can combine these two together. This is the theta function of the Gaussian, e to the minus pi dot squared at t times t to the s plus t to the 1 minus s. That's a common ingredient of both of them, dt over t, minus, let's see, what's the f of 0? F of 0 is easy. The Gaussian of 0 is 1, so there's a minus 1 over 2s. And f hat is f, so this is also 1 over 2 to the 1 minus s. So far, so good. What do you notice about this formula? Is there anything symmetric? Is there any symmetry?
S1 minus s, so like
Yes,
around half.
exactly. This is symmetric in s goes to 1 minus s. Therefore, so is this. And that is the meromorphic continuation. This is the classical meromorphic continuation of the Riemann zeta function. But the point that I want to make, and this is what's in Tate's thesis, is it's something very general. It has a unique analytic continuation, but you can get it through lots of different test functions, uncountably many different test functions. It doesn't have to be just the Gaussian. Okay, let's take a 5-minute break and look at the consequences of this miraculous formula when we come back. Okay, so you had asked about the Adels appearing here. So this is 1950, John Tate, who just recently passed away. So the interpretation of this is that there's a completed zeta function, which is traditionally denoted C, which is a product of local zeta values. These could now be called places instead of primes. There's a prime at infinity, which is the local places. And the infinity place is the function 1/2 or not, the 1/2 doesn't really matter, pi to the minus s over 2 gamma of s over 2. And the other local values are the Euler product values. So this is 1 over 1 minus p to the minus s. And what Tate really did is these are the same function, the same type of function. They come from a p-adic Mellin transform. So there's an Adelic Poisson summation, and when you compute a p-adic Mellin transform, you get literally this, and the p equals infinity adic Mellin transform is what we computed. Okay, so maybe that's all I'll say about that, except to give you hints that there's actual structure here.
Perfect. I'm happy. My day's made.
Okay, good. So that's why Tate's thesis was such a big, breakthrough. Anyway, why do we care? We're doing all this stuff. Where are the primes? Where are the primes in any of this? Where are the primes? Where are the primes? So here's what we need to know. Let's look again at the zeta function, and let's put in the Euler product. So this is, again, only for a real part of s bigger than 1, where we have a convergent product, 1 minus 1 over p to the s inverse. Right? So they're the primes. They're there. How do we get them? How do we get at them? Euler already showed us a little bit of how do we get at them. We take the logarithm. So log of zeta is a sum over the primes. Log, so negative log. Now we're worried about complex logs. Now we have to think about what we mean by this. But if real part of s is bigger than 1, then all of these numbers are an absolute value less than 1. So we can mean the standard complex log. In other words, the one that's defined perhaps by the power series. So this is a sum over primes, a sum over, and for each prime, what's log? Negative log of 1 minus z. Is this right? It's z plus z squared over 2 plus z cubed over 3 plus z to the 4th over 4 and so on. I think that's right. Yeah, because if you differentiate both sides, on this side you get 1 over 1 minus z, and on this side you get the geometric series. Okay, so this is 1 over p to the s plus 1 over p to the 2s over 2 plus 1 over 3 p to the 3s and so on. And that's a convergent series for each of them. Yeah, you guys are happy with that? But now we can differentiate both sides. ddz. dds. So here, what's the logarithmic derivative? Of course, it's just zeta prime over zeta. And here, so each of these factors is e to the minus s log p. And if I differentiate that, so under dds, I get the same e to the minus s log p times the chain rule, a minus log p comes down. So I'm just computing the derivative of p to the minus s. The derivative of p to the minus s is just p to the minus s times negative log p. And this is, again, calc 1 or something. Okay, so now I have a sum over the primes. The first term is negative log p over p to the s. What's the next term? Well, this is the same thing, except instead of s, I have 2s. So I get a derivative which is negative 2 log p over 2 p to the 2s. And negative 3 log p over 3 p to the 3s. And so on. So this is negative. The minus signs we can pull all out. The 2's you see cancel on top and bottom, and so do the 3's. And let's write this as a sum over all integers and capture which integers arise with a coefficient. So let's call this lambda of n. So this is the multiplicity with which n to the minus s arises here. This is called the von Mangoldt function. Von Mangoldt function. So what is it? So when do we get a contribution of n to the s? Well, look, we're summing over primes, and the sum over primes only sees prime powers. So if you're not a prime power, you don't occur in this summation at all. Does everybody see that? So if you have a prime power, then something happens, but if you're not a prime power, then the answer is 0. Does that make sense? And if you are a prime power, if you're a p to the k, then what's the coefficient in front of p to the, what's the coefficient of 2 to the s? Or 2 to the minus s? How do you get a 2 to the minus s in all this sum? Yes, somebody was saying, Theorem?
Log 2,
Exactly.
log p.
So there's a contribution of log p, and it's just log p for every single prime power. You get a factor of log p, and anything that's not a power of a prime, with k at least 1. Anything that's not a power of a prime, so 1 to the s doesn't occur here, because 1 is not a positive power of a prime, of a fixed prime. Does that make sense? So this is how we can access, this together with Perron's formula is how we can access primes. Why? Let's take a inverse Mellin convolution. So here's the next observation. The next key observation is to look at an inverse Mellin convolution. So I think we saw this before. If you take two Fourier transforms and you multiply them, and then you take the inverse Fourier transform, do you remember what happens? Did we talk about this? I think we did. No, we didn't talk about this. Should I make an exercise out of this? No, I won't. We didn't talk about convolutions at all? No. Okay. Well, okay, never mind. If this doesn't make any sense to you, then forget it. We don't need to know what that is. You'll see later, slightly later, why it makes sense to do this kind of thing. But here's what I want to do. I want to take the function zeta prime over zeta. I guess let me move this minus sign to the other side. What I really want is this then. So I'll take the function negative zeta prime over zeta at s. I'll multiply it by some test function. In fact, let's make this the Mellin transform of something. So I'm taking two Mellin transforms, two functions of s, I'm multiplying them, and I'll take a Mellin inverse transform, x to the s ds, integrated over some vertical line with 1 over 2 pi I thrown in for good measure. Let's say this is an entire function. Entire, nice decay properties. Okay, I just want to compute this integral. And I'm going to compute this integral in two ways. So far, so good. So this is like taking two functions, multiplying them together, and then taking an inverse transform. And what we'll get is a convolution of the two functions, but never mind, that's general nonsense. Let's do the calculation. The calculation will tell us what to do. we're in the region where this thing has absolute convergence, right? Real part of S is equal to 2. This is all only if real part of S is bigger than 1. So we're within this region. So we can put in the definition. By the definition, we have 1 over 2 pi I, integral over a vertical line 2, a summation over the positive integers, von Mangoldt function, this log of on the primes and 0 elsewhere, over n to the s, over n to the s, times phi ds. Do you buy that? I haven't done anything. All I did is I put in what zeta prime over zeta is and put the n to the minus s, grouped it with the x.
Is
Nick.
lambda a character? Like, is that a Dirichlet Dirichlet function?
This psi?
No, the lambda then.
It's not a character because it's not multiplicative.
Okay.
If I take n1 times n2, unless they're, it's just not, yeah.
Okay.
A, it doesn't have absolute value 1. B, it's not a homomorphism. It's just some weird function. But it's exactly this weird function that will capture the primes for us. So it's not a Dirichlet L function. It's some very different kind of object, this series. It's a Dirichlet series, but it's not a Dirichlet L function because the lambda is not a Dirichlet character. It's a Dirichlet series because Dirichlet series just means any complex numbers over n to the s summed up. Okay. Now again, assume we can interchange orders. I said phi was nice, so let's interchange orders. So I get lambda of n, and then what do I get here? Do you remember so phi was the Mellin transform, so phi tilde of s, I mean integral from 0 to infinity of some nice phi of u to the s du over u. And how would I get phi of u back? I'm reminding you of the inverse Mellin transform formula. It would be to take this thing and multiply by u to the minus s and integrate integrate ds. Does that ring a bell? And so when I pull this summation out, what am I left with? I'm left with 1 over 2 pi I integral over some vertical line phi tilde times u to the minus s, where u is n over x. So this will be phi of n over x. Does everyone see that? So now let's imagine, so let's bring things down to earth just a little bit. So here's an example. Example, phi of x is the indicator function of x being less than 1. You remember what phi tilde is? Remember what the Mellin transform of the indicator function of 0, 1 we did at the very beginning? You can look back at your notes, or I can scroll up.
It's 1 over s.
1 over s. Beautiful. 1 over s. Okay, so this function you actually can't do this with without a whole lot of technical difficulty, which all the old books have all these technical difficulties. They don't do things in smooth form, and it's I learned from our colleague here, Henrik Ivanets, that you must do everything in smooth form. Even some of his books, by the way. Not to wag a finger at him. Anyway, moving on. So let's say that's what this was. Okay. So this is phi of x is the indicator function that x is less than 1. Well, that's the this is the indicator function in this example. That's the indicator function of n over x being less than 1. Which is the same thing as n being less than x. In other words, in this case, this function would be a sum over n less than x of the von Mangoldt function. In other words, it's a sum of log 2 plus log 3 plus, well, let's see a graph of this then. In fact, what would this look like as a graph? So this as a function of x, this has a name, by the way. This is called psi of x. It's usually called Chebyshev's function. Whether you put a t or not, Chebyshev function. And it's very closely related to the prime counting function. That's why this function is going to tell us the prime number theorem. Okay, so you go along and it doesn't do anything until it gets to 2. At 2, you get a jump of how high? So this is psi of x versus x. So psi is 0 until you hit 2, and at 2 you get a jump of
Log 2?
log 2, exactly. You get a jump of log 2, and then you're flat until you hit the 3, and by 3 you get a jump of how much? Log 3, okay, good. Then you get to 4. What happens at 4? We're flat at 4? 4 is a prime power. It's a power of the prime 2, so we jump by log 2. Awesome. So we jump by log 2. Then we get to 5, and we jump by log 5. Then we get to 6, and we jump by log 6. We jump by nothing. 6 is not a prime power. It's 2 times 3. We stay flat at 6. Then at 7, we jump by log 7. At 8, we jump by log 2. At 9, we jump by, whoops. At
Log
9, we jump by, well, now I'm getting into, okay, you see what's going on. So this is this function, this step function. And this step function will tell us everything we want to know about the primes. I have to explain, so fact, which I will prove for you, I'm running at low on time for what I wanted to say. Fact is that this Chebyshev function grows asymptotically. You see, we bumped everything up by a factor of log. Instead of counting primes, we're counting log primes. So this is asymptotic to grows like x if and only if the prime counting function grows like the logarithmic integral of x, which itself is asymptotic to x over log x. So you see, we bump things up by a factor of log x locally at every prime and prime power, but the prime powers contribute nothing. Maybe I'll make that an exercise. Here's a nice exercise. What number are we up to? 4? Maybe? Exercise 4 is psi of x, which, if you want to write it like this, psi of x is a sum over primes and prime powers less than x of log of p, right? That's the same thing. We're just seeing what primes and prime powers. Every time you have one of these, it contributes log p. This is equal to just the sum over the primes themselves of log p, less than or equal to, less than, I don't care. Oops. Take x to be not an integer, and it won't make a difference. Log p plus an error, which is of size, let's say, x to the 1/2 plus epsilon. So all those prime power contributions, the contributions from the 4s and the 8s and the 9s, contribute nothing to the main objective. Okay? So far, so good? So that was one side of this calculation. One side of this calculation, let's come back to this calculation. The sum over n greater than or equal to 1, von Mangoldt of n, phi of n over x, was this integral. This integral. Let me zoom out so I can see it. Good. Now I can see both. 1 over 2 pi I, integral over a vertical line, and negative zeta prime over zeta of s, phi tilde of s, x to the s, ds. Okay. That's one calculation. In order to get anything, you have to calculate the same thing in 2 different ways. So one calculation was to put in the definition, and out comes this. What's another way we can analyze this integral? This again is an integral over the vertical line too. Pull it. If we pull this integral all the way back, we encounter poles. Where do we encounter poles? Zeta prime is a nice function. What's that, Nick?
Negative even integers.
Those will be poles, but more generally, where do we encounter poles? So let's say phi hat is entire, just for argument's sake. We only encounter poles where zeta prime over zeta has poles. So we encounter poles at poles of zeta prime over zeta. But this has poles if and only if. When does the logarithmic derivative have poles? You remember what happens to a logarithmic derivative? Thomas? Just guess.
Whenever it's 0 or a pole, right?
Yes, exactly. That's exactly when zeta has a pole or is equal to 0. This is why we care crucially what the zeros of the zeta function. We don't care about the zeros of the zeta function. We care about the poles of the logarithmic derivative of the zeta function, which happen to be the same thing. Okay? We only care about poles, not zeros, poles of zeta prime over zeta, which happen to be mostly, except for this one example. There's a pole at s equals 1, right? There's this pole at s equals 1, which happen to be mostly zeros of zeta. That's why we care about zeros of the zeta function. We're starting to see what they do for us. Okay, so let's do the contour pull, and let's do it, not exactly rigorously. So if we pull contours, what do we get? We get here, every time we have a pole, so we have this pole at s equals 1, right? Pole at s equals 1 of zeta. Zeta has a pole. Zeta has a pole at s equals 1. It has zeros. I don't know where the zero, at the moment, I don't know anything about where its zeros are. Let me be crude. I know that there aren't any zeros this way. We already proved, recall that if the real part of s is bigger than 1, if we're in the region of absolute convergence, then the zeta function does not vanish because of the Euler product formula. We have a convergent product, none of the terms is 0, the product's not 0. So over here, zeta is not 0. I know I have a pole here. I don't know yet. We'll see in a second. We'll get more information. I don't know what happens here. So let's just, when we pull contours, now what's the contribution? What's the residue of zeta prime over zeta? Do you remember the argument principle? That's the beauty of logarithmic derivatives. We don't need to compute any residues. It's 1 if you have a 0 and -1 if you have a pole. Recall the argument principle. The residue of any logarithmic derivative is 1 if the thing was 0 and -1 if the thing had a pole. So we don't have to compute any residues. So if we pull contours, this integral is equal to 1 over 2 pi I, integral over, let's say the real part is -1,000, but in a second we'll take it all the way, we'll send it all the way away. Negative zeta prime over zeta, phi tilde of s, x to the s, ds, plus all of the places where we have zeros. So let's call these zeros of the zeta function, rho, where zeta of rho is equal to 0. This contributes a +1 to the zeros, but we have a minus zeta prime over s. So it actually contributes a -1 times phi tilde of rho times x to the rho. And we have one more pole, and that's the pole at s equals 1. That's not a 0 of the zeta function. That's a pole of the zeta function. That would contribute -1, but with that minus sign, it contributes a +1. So this is the term s equals 1. So this has a residue 1. Then there's phi hat at 1 and x to the 1. And let's send this to infinity and forget about this integral. So let me write these two formulas sort of side by side so that you can see why this is literally Poisson summation on the primes. Poisson summation on the primes. On one hand, I have a sum over the positive integers of the basically prime indicator function, but bumped up by log, and you throw in the prime powers, which are minor nuances or annoyances, depending on nuisances. Maybe that's what I want to say. Times some test function. And that is equal to x to the 1 times phi hat of 1 plus a sum over all the zeros of the zeta function. I guess minus, I can put the minus sign here, minus phi tilde of rho times x to the rho. And that is a sum over the primes. This is a sum on primes. And this is the dual sum. Dual sum on zeros. And that is why the zeros of the zeta function are dual to the primes. This is a duality. This is an identity that holds for general test functions. With one side phi, on the other side it's Mellin transform. So next time we're out of time, we're going to see this identity in actual real life. And then we have to deal with if we want to prove. So what we want to prove in the case if phi, so what we want, now we're almost there. What we want is if phi of x is this indicator function. Of course, we can't apply it to the indicator function. We really can't apply it. We'd be missing terms. Then this whole thing will be psi of x. And we want that to be asymptotic to x. Where are we getting our x from? Where do we have a term x to the 1? Right there, the pole. The pole at s equals 1 is exactly why the prime number theorem is what it is. And so what we need is for all of these terms to be lower order. So we need the real parts of all of these zeros to be less than 1. And then we have to be able to add them up and so on. Okay, so we need some information. So it remains to show, and this is effectively what Riemann, all of this is sort of a modern reinterpretation of everything that's in that one paper of Riemann's. It's like 8 pages. It's amazing. Remains to show that all of the zeros have real part strictly less than 1. And if they all had real part a half, which is of course the Riemann hypothesis, then the error term would be square root cancellation, which is as good as it could possibly be. If all the zeros, the Riemann hypothesis is that all of the non-trivial zeros, there's some trivial zeros that we'll talk about, all of the non-trivial zeros lie on the central line of symmetry of the zeta function. Real part of S is 1. Okay, hopefully I have not gone too fast and stretched you too far, but we finish next class with the prime number theorem.